Welcome to this lecture on section 2.3 on homogeneous equations and with constant coefficients. So this section is about solving, getting general solutions for differential equations that are of this form. So this is a linear differential equation because the dependent variables y and all of its derivatives appear as a linear combination in this equation. It's homogeneous because the right-hand side is 0, and it has constant coefficients. So all of these coefficients of the derivatives and of the function y itself, they're all just constants. So these are all constant terms. So this is a linear homogeneous equation with constant coefficients. And the technique we'll learn in this section is how to get a general solution for this type of equation. And the idea is very simple. So it's based on the following. We consider this function, y equals e to the rx. And we'll see that every solution of this, this differential equation is going to be of this form. So we'll be able to get all solutions. We'll get a set of solutions which we'll use to then form the general solution. So consider this function. When we take the derivative of this function, we get this term. So we get an r that pops out from the chain rule. We take the derivative again, that gives us another r that pops out, so we get r squared, and so on. So when we do the nth derivative, we'll get r to the n e to the rx. And now substituting that into this differential equation, 1. So substituting this into 1, what do we get? We get, so this y, the nth derivative of y is this, so we substitute that there, and so on. So the first derivative is given by this term here, so we substitute that there. And finally, the function y itself is given here, so we substitute that there. Now, we have this e to the rx appearing in every term of this equation here, so we can cancel these all off because e to the rx is never 0, it's always positive. And when we divide by e to the rx, then we're given this equation here. And this term on the left, this is just a polynomial with degree n. So what this equation is asking us to do is to find the roots of this nth degree polynomial, because we want to find the values of r so that this equation is equal to 0. And this equation here is known as the characteristic equation of the differential equation 1. So since this is an nth degree polynomial, it has n roots where we do count the multiplicity. So it's possible that we have the root appearing more than once when we're looking at these n roots. So some of these roots may not be distinct. So we might have repeated roots in this list. And also, to make things more complicated, these roots could be real numbers, or they could be complex numbers. So those are two options. So for example, x squared plus 1 equals 0. So if we look at x squared plus 1 equals 0, then the solutions to this are going to be minus I or plus I. So it'll be plus or minus I. So that's why we sometimes will need to consider complex roots of this characteristic equation. So that's where we get complex roots. But let's start with the simplest case. So distinct real roots. If all of our roots of the characteristic equation are distinct real numbers, then we can show that each of these functions is going to be a solution. So that's not surprising. But what's more important is that these functions are going to be linearly independent. So there's not going to be any redundant solutions in this list of solutions. And since the differential equation is order n, that's all we need. We need n linearly independent solutions. And so that this gives it to us. And so therefore, this is our general solution, where we form this linear combination of those solutions. So we have C1 times the first function, and so on up to Cn times the last function. And I'm missing a plus sign here. Let me insert that plus sign. Okay, inserted the plus sign. Okay, so there's our general solution of the equation when all the roots are distinct and real. So let's do an example of this type. So first of all, we write down the characteristic equation. Characteristic equation. And so we replace the y double prime with r squared. We replace the y prime with r. And then we just replace y with 1. So this is our characteristic equation. And we just need to find the roots of this equation. So let's see, I think we can factor this equation. So we're going to get r. So we need two numbers that multiply to be minus 10 and add together to be 3. So that'll be like minus 2 and plus 5. Yeah, so therefore the roots are going to be 2 and minus 5. So the solutions that we have then are going to be y1 is e to the 2x, and y2 will be e to the negative 5x. So that's what those two roots tell us. We get these two solutions here. And so therefore, the general solution is, or a general solution is y of x is equal to c1 e to the 2x plus c2 e to the negative 5x. Okay. So that's how easy it is. You take your linear differential equation with constant coefficients, that's homogeneous. You write down the characteristic equation. You solve it by factoring, for example, and then that will give you the roots. And if they are real and distinct roots, then we know exactly the particular solutions that are linearly independent, and therefore that gives us our general solution like that. So pretty straightforward. Doesn't even require any integration, doesn't even really require differentiation. So it's a very simple way to solve a lot of different types of differential equations that are of this form. Okay, so the first thing that could make it a little bit more complicated is if we have a repeated real root. So imagine that we have a root r, so one of the n roots that is repeated k times. So then what do? Well, we can't just have e to the r k times because that's clearly linearly dependent, right? That would give us a bunch of redundant solutions. So we don't do that. But it turns out that in this situation, so e to the rx is a solution, but also if you multiply e to the rx times x, then you get another solution of the homogeneous differential equation. And these are linearly independent. And you can keep doing that up to this number of times that it gets repeated. So this is the first one, that's the second one, and you keep going up to x to the k minus 1. So that'll give us our kth solution, so 1 to up to k solutions. And all of these particular solutions are actually linearly independent. And they'll also be linearly independent with different roots as well. So we can add this to our set of linearly independent solutions of 1. And what that means for our general solution is we would add a term that looks like this. So these, you may call these different numbers, but the idea is that we just add a linear combination of those k solutions to our general solution. So that's the idea. Okay, so let's do an example of this. So here the characteristic equation is going to be 4r squared minus 12r plus 9 equals 0. Okay, well, so this is a little bit more tricky to factor to find the roots. We could try using the quadratic formula. So let's try that. It's a good thing to remember how to use. So this is going to be minus b plus or minus the square root of b squared minus 4ac divided by 2a. So what do we get? This will be minus 12, because b is minus 12, plus or minus the square root of minus b squared, so that's 144, minus 4 times a, which is 4, times c, which is 9. Okay, so there's our square root term, and then divided by 2a, so 2 times 4. And what do we get? We get 12 plus or minus, and now 4 times 4 times 9, that is 144. So we get plus or minus the square root of 0, and then this is divided by 8. And so we end up getting, let's see, that will be 3 over 2 and 3 over 2, because it's plus or minus 0. So when this term here, b squared minus 4ac for a quadratic polynomial, when this is 0, that means that we have a repeated root. So there's our repeated roots. It's 3 over 2 and 3 over 2. Okay, so that means that y1 equals e to the 3 over 2x, and y2, so when it's a repeated root, you just multiply by x, like that. So these are linearly independent solutions. And so therefore, a general solution is, so we just do a linear combination of those. Let's see, I'm just going to move this out of my way, like that. So a general solution is y of x equals c1 e to the 3 over 2x, 3 over 2x plus c2 x e to the 3 over 2x. And that is our general solution of that differential equation. Okay, so that's how it works when you have a repeated root, is you just need to multiply by x for each repeated root. And that will give you a set of linearly independent solutions that you need. Okay, let's do another example. Okay, here the characteristic equation is r to the 4th minus 8r cubed plus 16r squared. Okay, so first of all, I see that I can factor out an r squared. So that'll leave me with r squared minus 8r plus 16. Okay. And let's see. So this term is actually a perfect square. It's r minus 4 squared. So there's our factorization that we need. So the roots are going to be 0, 0, 4, 4. So therefore, let's see, what did I say? So therefore, what are the linearly independent solutions? So we get y1 is equal to e to the 0x. So maybe I'll write that. So e to the 0x, but that's just equal to 1. So e to the 0 is 1. Y2, so this is also going to be e to the 0x, but it's repeated, so we multiply by x. So we get x e to the 0x. That gives us x times 1, which is x. Okay, I'll just put the other ones here. So y3 is going to be e to the 4x. And then we get another root of 4. So we multiply that by x. We get e to the x times e to the 4x. And so therefore, a general solution is y of x is equal to c1 times 1 plus c2 times x plus c3 e to the 4x plus c4 x e to the 4x. Okay. So that's the idea. Just divide those, separate those a little bit. So that's how we deal with repeated roots. So each root will give us a solution of the form e to the rx, and if it's repeated, then we just multiply by x, the number of times that the root is repeated. So if there had been another root, for example, if there had been 0, 0, 4, 4, 4, then we would have had a y5 that was, so if we had another root, for example, we would get y5, it's equal to x squared e to the 4x, for example. So just to make that clear. Okay, so I'm gonna erase that because that's not part of the actual solution. Okay, so that's the story about real roots, and now we have to deal with what happens in the case that we have a complex root. So what is a complex number? A complex number is a number that is of this form, a plus I times b, where I is the square root of -1. So I squared is equal to -1. And so this is referred to as the real part of R, and this is the imaginary part of R. Okay, and you may be, from some of your other classes, you may be more used to using J instead of using I, but in mathematics, we tend to use I for the imaginary number. But I think in engineering, for example, it's typically J is used for the imaginary number. So just to make that point. Okay, so how are we going to turn a complex root into a solution of this differential equation? It's based on this very famous formula called Taylor's formula, which says that if you take E and raise it to the power of I times theta, then that is a complex number. The real part of this complex number is cosine theta, and the imaginary part of this number is going to be sine theta. So we get cosine plus I times sine theta. And this is quite a remarkable formula. It's not at all intuitive that when you do the exponential of I theta, that you would get these trig functions like this. So how can we see this? I think it's a good idea to understand, where does this come from? How could this possibly be true? So the proof really comes from using the Taylor series expansion for these three functions: e to the x, cosine theta, and sine theta. So e to the x has a Taylor series that looks like this. You may be familiar with this from your calculus 2. So e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24, and so on. If you look at the Taylor series for cosine, it goes as follows. It goes 1 minus theta squared over 2 plus theta to the 4th over 4 factorial. So notice we're skipping some of these because the reason is because when you take the derivative of cosine, once you get sine, and if you substitute 0 into that, you get 0. So that's why we're losing like the theta cubed, theta to the 5th, and so on. Those are just 0. So anyway, we get this, and then we get this sort of alternating sign pattern here as well. And that's due to when you take the derivative of cosine twice, you get negative cosine, and so on. And then for the sine theta, we get kind of the opposite. So now we're getting, instead of the even powers of theta, we're getting the odd powers of theta here. But it's very similar. We get theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on. Anyway, so these should be very familiar Taylor series formulas. And this is how we can prove this formula here. So let's take this e to the x, and we'll substitute in I theta into there. So this x gets replaced with I theta, x squared becomes I theta squared, x cubed is I theta cubed, and x to the 4th is I theta to the 4th. And then now we can use the property of I, that I squared is minus 1. So here we're going to do I squared theta squared. So the I squared becomes minus 1. Here we're doing I cubed. So we get negative I in there. So there's the I squared becomes negative 1. And then we have another I after that. And if we do I to the 4th, then we get I squared squared, so that's minus 1 squared, and that becomes 1. So this is what we get when we substitute in I theta into that Taylor series. Then we can group together the terms in here that do not have an I. So there's no I here for these terms, so we'll group those together. And then we'll group together the terms that have an I. So we get plus I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial and so on. And then we just observe that this is the Taylor series for cosine theta, and this is the Taylor series for sine theta. And that is essentially the proof. So you can prove this formula through Taylor series. Very remarkable formula. And it has this especially nice formula when you plug in theta, or so when you plug in pi for theta, then you get e to the I pi is going to be cosine pi plus I sine pi. And cosine pi is -1, and sine pi is 0. And so we get e to the I pi is equal to -1. And often people will bring this 1 over here, and we get this very beautiful formula that e to the I pi plus 1 is equal to 0. Really, really remarkable to see all of these fundamental numbers. So E is this number like 2.7 something. It's an irrational number. We have pi 3.14 and so on is an irrational number. We have this imaginary number I. So I squared is -1. And then we have these, obviously very important number. 1 is very important. Multiply anything by 1 and it doesn't change. And then we have 0, also a very important number. If you add 0 to anything, it doesn't change. So this is sometimes called the multiplicative identity, and this is the additive identity. So all of these very fundamental concepts for mathematics coming together in a single equation. It's really, really remarkable. Almost hard to believe. So here's a bit of more of a geometric idea of what's going on with complex numbers. So often we write complex numbers in a plot like this. Oops. We write complex numbers in a plot like this using Cartesian coordinates, and we refer to this as the complex plane. And we write the set of complex numbers using this notation. There's also a similar notation for the real numbers. So real numbers are often written like this with a double-backed R like that. But for complex numbers, we use this double-back C. So how do we put a complex number in here? So the x-axis is going to refer to the real part. So this is like the real part of the complex numbers right here. And this is the imaginary part here. So we have the real part and the imaginary part like that. So if we have A plus I times B, we plot that as this point right here, whose x coordinate is A and whose y coordinate is B. So that is how we think of this point in the complex plane. And what is this e to the I theta then? So we know e to the I theta is cosine theta plus I sine theta. So this is a point whose x coordinate is cosine theta and whose y component is sine theta. And I'm just gonna let my dog in because she's scratching at the door. 1 second. Okay, my dog just wanted to come in. Where did she go? Here she is. So this is my dog. This is my dog, Chana. I think she's made an appearance before. Yeah, this is Chana. All right. So, what is the point whose x coordinate is cosine and theta and whose y component is sine theta? This is the point on the unit circle where we take the angle theta here, and that gives us this point. So we can think of e to the I theta as being a point on the unit circle in the complex plane, where the theta tells us how far around this unit circle we are. Okay. So what does this mean for solving the differential equation? So if we look at the characteristic equation and we find that it has a complex pair of roots. So if there's a complex root, a plus I times b, then we're guaranteed to have the corresponding a minus ib root as well. And that sort of comes from the quadratic formula, right? So there's, if you take the square root of b squared minus 4ac, if that ends up being negative, then you're going to get this plus or minus I times something. So that's why we always have, if we have one complex root, we have the corresponding complex root as well, which is called the conjugate. So if you change the plus to a minus or minus to plus, that's called the conjugate number. So if we have this complex pair of roots and if it's unrepeated, then this actually indicates that we have these two linearly independent solutions of the differential equation. So the a tells us what this e to the ax is. So that'll tell us what the exponential should be here. And the b tells us what this number is here when we do the cosine of bx. So the b gives us that number there. So the a goes there and the b goes there, and we get one for the cosine and one for sine. And so these are also going to be linearly independent with other possible functions like e to the rx and x to the k, e to the rx, and so on. So these are going to be linearly independent with all those other functions that we're getting from other roots. And so that means that we just need to add a linear combination of these two functions to our general solution. So here's a linear combination of those two functions. Now, where does this come from? So I guess we already know from the Euler's formula that this is somehow related to. So we're going to be doing e to the rx, and that's going to somehow give us these trig functions. And how does that work? So if this is our root, so e to the a plus or minus ib times x. So if we break this up, we get e to the ax times e to the plus or minus, this should be an I, e to the plus or minus I times bx. And then by Euler's formula, this e plus or minus I times bx is going to give us cosine of plus or minus bx plus I times sine of plus or minus bx. And since cosine is an even number, cosine bx is cosine bx, and cosine minus bx will also be cosine bx. And that's because cosine is an even function. Even function means that if you reflect it across the y-axis, then you get the same thing. And sine is an odd function. So when you do sine of negative bx, so if you flip sine across the y-axis, then that's the same as flipping it upside down. And so sine of negative bx is going to be negative sine bx. And so we end up getting this. And so notice that we're getting like two solutions here. We're getting a cosine bx plus I sine bx, and we're also getting cosine bx minus sine bx times I. And so we end up getting these two solutions, and we could use those two solutions, but it's simpler to to break it up and do e to the ax times cosine bx as one solution, and then e to the ax times sine bx as the other solution. So that's how we get our two linearly independent solutions like that from using Euler's formula. So, okay. So let's do an example. So here the characteristic equation is r cubed plus 3r squared plus 4r minus 8 equals 0. Okay, so how are we going to solve this? Well, in this form, it's a little bit tricky to see how to factor this. We see that there's this minus 8 here. So we know that we should have something like 1 minus 1, 2 minus 2, or 4 minus 4. One of those is going to be a root. So we can test each of them. So we could start with r equals 1 and see what happens when we substitute that in. So r 1 cubed plus 3 1 squared plus 4 times 1 minus 8. And that would be 8 minus 8, which is 0. So that means r equals minus 1 is indeed a root of this polynomial. So we can then divide the r minus 1 from this polynomial. So we can do some long division here. And this will give us the other factor. So let's do this long division. So, so I need to do r squared times r minus 1 to get an r cubed. So this will give me r cubed minus r squared. And then we subtract that, and that will give us 4r squared. And then bring this term down. So now we have 4r squared, so that means we're going to do plus 4r to give us the 4r squared, and then minus 4r. So 4r times r minus 1 gives us this. And then we subtract that, and that gives us 8r, and then bring the minus 8 down, and we get plus 8. So that gives us 8r minus 8, and a remainder of 0, which is what we expected. So we knew r equals 1 as a root, so r minus 1 should divide evenly into this polynomial, and we end up getting r squared plus 4r plus 8. So therefore, r cubed, let me just copy it. So this is equal to r minus 1 times this quotient. Okay, so, so now we need to factor this part here, or find the roots of this part. So there's a couple different ways to do this. Let's use the quadratic formula again. So, so what is the quadratic formula for that second part? So now I'm just focusing on this part here now. So what are the solutions? So we know we have. I guess maybe I'll write it down this way. So this is equal to 0. So that tells us that r minus 1 is 0, or r squared plus 4r plus 8 equals 0. Okay, so now I'm just going to focus on this piece. So we can use, again, the quadratic formula. So minus b plus or minus square root of b squared minus 4ac over 2a. So we get minus 4 plus or minus the square root of b squared, which is 16, minus 4 times 1 times 8, which is 32. So we're going to take the square root of that, and then we're dividing by 2. Let me just add another page here. Okay. So what do we get? Let's see. So this will be minus 2, and then plus or minus the square root of negative 16 over 2. So square root of negative 16 is going to be 4 times the square root of negative 1, which is I. So we'll get minus 2 plus or minus 4i over 2, which is 2i. Okay, so maybe I'll fill this in a little bit. So this is our final answer. So this is minus 2 plus or minus 4i over 2. Like that. Okay, so there's our roots now. So therefore, r is equal to 1, or it's equal to minus 2 plus or minus 2i. So then what are the solutions? So therefore, y1 is equal to e to the rx, so e to the 1 times x, that's e to the x. And then this second one, so now we have a complex pair of roots. So we know this is going to be e to the negative 2x, and then this 2 will give us the sine and cosine functions. So we'll get y2 equals e to the negative 2x. And maybe I could highlight this. So negative 2 goes there. And then cosine 2x. And that 2 comes from this 2. Okay, and then we get the same thing for the next one. So y3 is e to the negative 2x, but now it's sine 2x. Okay, so this negative 2 goes into this exponent, e to the negative 2x, and this 2, this imaginary part, goes here and here into the trig functions. So these are linearly independent solutions of the differential equation. And so therefore, a general solution is a linear combination of those. So we get C1 e to the x plus C2 e to the negative 2x cosine 2x, and plus C3 e to the negative 2x sine 2x. And that's our general solution. So that's how it works. So what did we do? We took the differential equation, we wrote down its characteristic equation, we found one root by just guessing. If we put r equals 1 in there, then it turned out that was a root. So then we just did our long division to get that, to divide out by the r-1 factor. And that gave us the other factor of this polynomial. So we get, r-1 is 0, or this other factor is equal to 0. And since that was a quadratic equation, we just used the quadratic formula to solve it. There is another way to do this, as I kind of mentioned briefly. You can do like a complete the squares trick, which maybe I'll show you at some point. But for now, I think this is a good approach, is to just use the quadratic formula to get the roots of that quadratic equation. And then once we know the roots, we write down the linearly independent solutions of the homogeneous differential equation, and then that gives us our general solution. So that's it. It's essentially just doing solving polynomial equations. So that's the most tricky part. And once you get the roots, then you just write down the solution based on the roots. Very, very nice. Okay, so there's one more case to consider. So, and that is the case of what happens if, oh, I forgot to write the number in here. So this is I think this is case number 4, right? So what was the previous case? Case 3, right? So this is the last case, case 4. So these are the 4 different things that could happen when you get roots of this polynomial, this characteristic equation. So the last thing that can happen is we get a pair of complex roots that is repeated. So repeated, say, k times. So what do we do then? Well, it's very much the same as when we had repeated real roots. In that case, for every time the root was repeated, we just multiply by x. And that's what we do here. So we take our first solution, e to the ax times cosine bx, and we just multiply it by x, k minus 1 times. So this is 1, and then this is 2, and so on. So this is the kth solution with x to the k minus 1. So that gives us k linearly independent solutions. And then we do the same thing with e to the ax times sine bx. So we just multiply it also the same number of times. So we get k solutions here, we get another k solutions here. So that gives us 2k solutions corresponding to the 2k roots that we get here. Because each one of these pairs is 2 roots, and we get k of them. So that gives us 2k roots in total. And we get 2k linearly independent solutions. So then we just add a linear combination of those solutions to the general solution. So, and that looks like this, right? Okay, so let's do an example of this one. Let's see. So the characteristic equation is r to the 4th plus 2r cubed plus 3r squared plus 2r plus 1 equals 0. So there's our characteristic equation. Now, let's see. So this is example number 20 from the book, and they actually, so this is kind of a more difficult polynomial to try to get the solutions of. And the suggestion that they say is to consider the following. So they say sort of a hint from the book was to expand, let's see, expand r squared plus r plus 1 squared. So that's the hint there. Okay, so let's do this. r squared plus r plus 1 squared and what do we get? Let's see. So we get r to the 4th. So that's this times this. And then we'll do r squared times r, and then r squared times 1. So we'll do it in that order. So we'll get plus r squared times r, it's r cubed, plus r squared times 1. So that's r squared. And now we'll do this term, r times r squared, r times r, and r times 1. So that gives us r cubed plus r squared plus r. And then finally we do 1 times r squared, 1 times r, 1 times minus 1, or 1 times 1. And that will give us r squared plus r plus 1. Okay, so we get r to the 4th plus 2r cubed plus 3r squared plus 2r plus 1. And that is exactly this characteristic equation right there. Yeah. So therefore, our characteristic equation so this tells us that r squared plus r plus 1 squared is equal to 0. Okay. So that means that the roots of this are going to be repeated twice. So what are the roots of this? So it's kind of like saying we get this is equal to 0 or this is equal to 0. That's kind of what's going on. So whatever the roots are of this polynomial, they're going to be repeated twice. So what are the roots of that? So let's see. Let's use the quadratic formula again. Minus 1 plus or minus square root of 1 minus 4 times 1 times 1. So that's 4 times 1. And then divided by, I guess I can put the other 1 there. And then divided by 2 times 1. So that'll be minus 1 over 2 plus or minus, and then that'll be the square root of negative 3. So we'll get I times the square root of 3 over 2. Okay, so therefore the roots are going to be minus 1 over 2 plus or minus I square root 3 over 2. And then that is repeated again. So we get another copy of this pair of roots. Like that. And so therefore, y1 is equal to e to the negative 1/2 times x. Maybe I'll just write it as x over 2 times cosine of root 3 over 2 times x. y2 is e, well, so it's repeated. So I guess let me follow the pattern I did in the description above. So since it's repeated, then we'll have the same thing again. Like that. So you see this is repeated here. So that means I'm going to get this again, but the second time I multiply by x. And that will give me a linearly independent solution. And then we do the same thing with, well, it's exactly the same, except I just replace the cosine with sine. So this is y3 and y4, and this will be sine. So y3 is this, and y4 is that. And so therefore, a general solution is y of x is equal to c1 times y1 plus c2 times y2. Oops. Plus c3 times y3 plus c4 times y4. And of course, it might be nice to sort of rewrite this. Why don't we do that? Let's rewrite this. So another way to write this that's a little bit more compact would be the following. So let me see. So first of all, there's a e to the negative x over 2 everywhere, so I can factor that out. So I'll get e to the negative x over 2, and then I'll have the cosine term will be c1 plus c2x times cosine root 3 over 2x. And then the sine term, we have c3 plus c4 times x times sine of root 3 over 2x. Okay, so that's kind of a more compact way to write the solution. Okay, and that is it. So thank you for watching, and let me know if you have any questions about this. Bye for now.